Initially, for problem number 12, I'm just anticipating problems that you guys might have questions on, but initially this one looks like it might be a difficult slope field problem to create. I don't think it's going to be, actually. So what I would do here is I would write x, y, and then I would write the slope, y over 2 times the cosine of pi x. So initially x is 0, y is 2. So when y is 2 I get 1. Cosine of 0 is also 1, so I get 1. So we draw a slope of 1, little line segment with slope of 1 right there at 0, 2. Okay, let's try 0. Oops, that's not a very good 0. Let's try 0, 5 halves. Okay, well, if I notice here that when x is 0, the cosine of pi times 0 is going to be 0. So anytime I get x is 0, the y value is going to be 1, because cosine of 0 is 1. But then 5 halves, I get 5 fourths then. So when y is 5 halves, then y over 2 is 5 fourths. When y is 3, y over 2 is 3 halves. Okay, so 5 fourths would be a little bit bigger than 1, so it doesn't make it really a nice, it doesn't make it super easy, but 3 halves also. Just make sure that, 1 1/4 here is bigger than 1 1/2, so that probably wasn't a very good one. 1 looks like that, just a little bit steeper than the 1, and then a little bit steeper than that one. You just have to make sure that the steepness goes up. Okay. And then when x is equal to 1/2, these are easy. This is the way I thought it was going to be. When x is equal to 1/2, all three of those, we get the cosine of pi over 2, and so therefore cosine of pi over 2 is 0, so all the slopes are going to be 0 there. So that's kind of nice. That makes it easy. Okay, so 0 slope, 0 slope, 0 slope. Okay, and then noticing when when x is equal to, let me erase some of this stuff here. When x is equal to 1, which is our last column of slopes that we need to fill in, when x is equal to 1, we get the cosine of pi. So the cosine of pi, that's going to be -1. So whatever we get when we plug in the y values, again, we already have the y values at 1, 5 fourths, and 3 halves. So you could try to find some patterns here. Again, we had 1, 2, we had 1, 5 halves, and we had 1, 1, comma 3. Okay. And so we just have negative, so -1 for the 1, 2, -1 there, -5 fourths there, so a little bit steeper than the negative. No, that's bad. A little bit steeper than the -1. That doesn't look very much steeper. Let me make the -1 a little bit less steep. Kind of like that. -5 fourths. And then the last one needs to be just a little bit steeper than the previous one. Okay, that looks pretty good. Alright. So that takes care of the slope field. Now it's asking us for part B, starting at 0, 2, use Euler's method with a step of 0.25 to approximate f of 1. So we have to get all the way from the point 0, 2. Let me zoom in a little bit here. So the point 0, 2 right here, all the way to figure out what's the value of the function when x is equal to 1. But we have to go in increments of 0.25. So we have 1, 2, 3, 4. Well, that's pleasant. So we get 4 times we get to use Euler's method. Oh, good grief. Well, I guess I'll need some room here, so let me erase some of this stuff here. Get rid of that. Do I need any of that? Hope not. Okay, so since I'm asking you to do it, I guess I'll do it as well. So we have our chart. We're using Euler's method, and we've got our initial value of our current xy at 0, 2. And then what's our slope? Well, our slope is, I could have used all that. I'll remember. Our slope is 1, okay, and then our y then is equal to our new y minus y1 is equal to slope times x minus x1, and our new y is equal to x plus 2, okay. I should have put that down here. No, that's alright. So our new y is x plus 2, and what do we want to find out? Well, we want to find out what is y at 1/4. Oh boy. Y at 1/4. Okay, well, y at 1/4 is equal to 1/4 plus 2, so 2 and 1/4. So now our new y value is, I guess we can put it right here, 2 and 1/2, so 2 1/4 would be right there. Gosh, software doesn't let me put those points there very well. Okay, so our that's our current now. Current. I really don't want to do all of this. I don't blame you for not wanting to do it all either. So maybe we'll do the first two and then we'll just check our answer at the end. Okay, so our current then xy, let me fill this in. So we have 1/4, comma, 2 and 1/4. That's our current position. Okay, so 1/4, comma, 2 and 1/4. And our slope there, when x is equal to 1/4, cosine of pi over 4. Oh, good grief. That is not a fun one. Just the slope. Okay, well, let's do it anyway. I told you we'd do one. Dy dx, so y prime at 1/4 equals y, which is 2 and 1/4, which is 9/4. 9/4 divided by 2. So we don't want to get too tricky here. We want to try to make sure we show all of our work so we get the correct slope. Multiply that by the cosine of pi over 4. Okay, multiply by the cosine of pi over 4. And times 1/2, so we get 9/8 times radical 2 over 2. So this would be one, once they start getting into irrational numbers, then you can use your calculator. Okay, so we have 9 times radical 2, and we're dividing that by 16. That's that. Oh, so that's 0.795. Okay, equals 0.795. That's approximately equal to. Okay, well, that's really nice because now we have a slope of 0.795, and we have to use that slope to come up with the equation of the line, and I really don't want to do that. That's just garbage. So I'll just have you maybe get that far and then just check the solution. Check the solution. I don't want to put you through that because I don't want to go through it either. Okay, well, that's 12a and b, so we're just going to check the solution on Euler's method. You'll never get a problem that you have to do that much math in this one problem. I've got a mark on my front of my screen here. So the next part, part C, I believe won't be as time consuming as part B, so let's take a look. Part C is asking us to find the actual solution to the differential equation. And let's rewrite this. I'm trying to figure out how I'm going to do this. Let's do this. Let's rewrite the equation y over 2 times the cosine of pi x. So this is one of those separable differential equations that you need to be able to solve, and you should recognize immediately that's this is a separable one. And if we're going to multiply both sides, we're going to separate the variables. We're going to multiply both sides by dx. We're also going to be dividing both sides by y over 2. So I'm going to do it like that. And then the dx's cancel, the y over 2's cancel, and when the dust settles, what you actually get on the left-hand side is 2 over y dy. Okay, so dividing by y over 2 is like multiplying by 2 over y. And then on the right-hand side, we get cosine of pi x, okay, dx. And then integrating both sides, we can see on the left-hand side, now we do get to use the ln's here. We get 2 times ln of y, absolute value, is equal to the sine of pi x, and that's divided by pi, and then we have plus c. Okay, so we're going to divide both sides by 2, so we should have really left that 2 on the right-hand side to begin with, equals sine of pi x over 2 pi plus c. And then now we have it in a position where we can do that flower power. We can raise e to this side, sine of pi x, again, over 2 pi. Now I could do this plus c out here, and that's equal to y, or I could remember that, how we do that, that plus c out here becomes a just c, equals c times e to the sine of pi x over 2 pi, and that's equal to y. So we need to use that initial condition 0 when y of 0 is 2, and that when we plug in 0 for x, notice here that when we replace 0 with x with 0, we're going to get sine of 0, and sine of 0 is 0. So this whole thing, when we replace x with 0, is equal to 0, and then y, when x is 0, is equal to 2. That was given to us. Okay, so therefore we see e to the 0, that's just 1, so that whole thing is 1, so we see that c has a value of 2. Okay, so that's the constant. And let's bring that way up here. So now we have the equation y equals 2, c, which is 2, times e to the sine of pi x over 2 pi. And it says evaluate f of 1. Well, this y equals f of x, so f of 1 is the same as y of 1. 2 times e to the sine of pi. Okay, now the sine of pi, you should know that that is 0. Okay, so when we replace x with 1, we get 0 again in our exponent, and so that makes sense because now we can get an exact value. 2 times 1 is 2. And that is our exact value of f of x when x is equal to 1. So that's part C, and that's it.